Hi, thanks for joining me. Today I'm going to be going over problem 1 from week 5 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. This is the problem we have for today. There are n people numbered 1, 2, all the way up to n playing a game. First, they're told a directed graph G exists with n nodes labelled 1 up to n. They are then allowed to discuss and decide a collective strategy amongst themselves before they are placed in a room and each person is given either a red or a blue hat. The room is designed such that the person I cannot see their own hat, nor the hat of any person J, such that there is a directed edge in G from I to J. They can see all other hats. All at once, each person guesses the colour of their own hat. If at least one person guesses correctly, the n people win, otherwise they lose. For which G can a win be guaranteed? So we have some directed graph G. So a directed graph, well, think back to graph theory. When you have a graph, something like this, maybe something like that. This is G, and these are our labelled edges, 1, 2, 3, 4, 5, say. And each of these edges has some direction on them, like so. Something like that. And so yeah, so for example, if this was G, then person 2 would not be able to see person 4's hat, because if we just read this sentence again, the room is designed such that the person I cannot see their own hat, nor the hat of any person J, such that there is a directed edge from I to J. So since there's a directed edge from 2 to 4, 2 can't see 4's hat. Similarly, 2 can't see 1's hat, or 5 can't see the colour of 2's hat, and so on. So is there a strategy so that they can guarantee a win? If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so I claim that they can guarantee a win if and only if G complement contains a directed cycle. So firstly, what is G complement? It just basically means you take the edges in G, you get rid of them, and then you add in any edges which weren't there. So you basically swap everything. So if there is an edge, you get rid of it, and if there isn't an edge, you add it. So for example, if G looks something like this, say, and we had like this, and remember we're allowed to have sort of double edges, I guess, or sort of loops like this. So then what would G complement look like? So G complement would have the same vertices, of course, and then basically wherever there's not an edge, so we don't have an edge going from this vertex to this vertex, so we include that. Well, we have both edges here, so there's not going to be any edge there. We have this guy going up to that guy, but we don't have this guy going up to that guy. We have this guy to this guy, so we're going to put this guy to this guy. And we have this guy to this guy, so we're going to put this guy to this guy. And we have neither edge from these two, so we're going to include both of those, like so. So this is how we get from G to G complement. So this is just an example, of course. Anyway, this is my claim, but of course I've got to prove it. So this is an if and only if statement, so I'm going to prove one direction first, then I'll prove the other. So I'm going to prove right to left. So I'm going to prove that if G complement contains a directed cycle, then we can guarantee a win, or there's a strategy in which we can guarantee a win. Now, what is this strategy? Well, let's denote our cycle firstly. So we'll call it x1, x2, all the way up to xk. So in other words, the directed edge from xi to xi plus 1, this kind of directed edge, is in the edge set, the directed edge set of G complement. Okay, and now what are these kind of edges from G complement? Well, it basically means that I can see J. So if this is vertex I and this is vertex J, because we've got this directed edge from I to J, it means that I can see the colour of J's hat. And that was kind of because of how G was defined. So the more edges in here, I guess, the better, because that way we have more information to our hands. So firstly, suppose we have this directed cycle here. So x1 goes to x2, x2 to x3, and so on, and then xk wraps around back to x1. I should perhaps put that there. xk, x1 is also in our edge set. How can we use this to prove that, or derive a strategy which is guaranteed? So what we're going to do is we're going to tell each of these the first k minus 1 xi's. So for 1 less than or equal to I less than or equal to k minus 1, xi is going to guess the opposite color to xi plus 1. So of course each of these hats are either red or blue. x1 can see x2, so if x2 was wearing a blue hat, then x1 would guess that their own hat is red. Now why does this work? Well, suppose this doesn't work. That means each of these xi's, so for each I between 1 and k minus 1, they all guess wrong. So that means, say, suppose x2's hat was blue, then because x1 guesses wrong, that means they've guessed red. So that means that their actual color is blue, because they see x2's hat, which is blue. They know that theirs is, so they guess the opposite, which is red, and if they're wrong, then of course their hat must be blue. What about x2? Well, their hat's blue, we know that. And if they got it wrong, that means they guessed red, but then that means x3's hat is blue. So that means x3's hat is blue, and so on. We can continue like this forever, and in fact, well, I say forever, we can do this k times, and then we'd be able to deduce that xk's hat is blue. So the strategy then would just say to let xk will guess the color on x1's hat. So they won't guess the opposite, they'll guess the exact color. Yeah, so let's just quickly go over that. We've got this x1 up to xk, and what each of these, the first k minus 1 xi's, they're going to guess the color opposite to the one in front of them. So if they're all wrong, then it must be that each of those k minus 1 guys have the same color hat, and therefore xk, in fact all of the k's will have the same color hat, so therefore xk guessing the x1 will, the color of the x1 hat, they're guaranteed to be right. So there's going to be at least one right, and therefore they're going to win. So this is a strategy that they can employ. So if G complement contains a directed cycle, this is how they can guarantee a win. So that proves right to left. Now let me clean up the whiteboard and we'll prove left to right. Okay, so now we want to prove left to right. So if there is a winning strategy, then G complement contains a directed cycle. And the way we're going to do this is by contradiction. So we're going to suppose G complement doesn't contain a directed cycle, and then we're going to prove that we can't actually have a winning strategy. So kind of proof by contrapositive, if you will. So suppose G complement has no directed cycle. What does this mean then? Well, it means that there must be a vertex with no outgoing edges. Now, why is that true? Because if you didn't have this, i.e. each vertex had an outgoing edge, well then you could just choose some arbitrary vertex and then keep going out of that to some other vertex and keep going out of that and so on, and you'd only have to do this at most n times because there's n vertices, say, in our graph, and because each vertex has an outgoing edge, eventually you'd have to find some sort of cycle by doing this, because there's finitely many vertices in our graph. So yeah, if each vertex had an outgoing edge, we could kind of continue this process, and therefore we'd end up with a cycle, which is not allowed. So G complement not having a directed cycle must mean that there is at least one edge, at least one vertex without an outgoing edge. So we're going to label this vertex Vn. There could be multiple choices for Vn, but for now we're just going to choose one of them. So Vn is going to be our vertex with no outgoing edge. Cool. Next thing we're going to look at is G complement without Vn. So we look at G complement, the graph, take out the vertex Vn and all associated edges, and then, well, this is still going to be a graph, a directed graph with no directed cycle, so we can apply the same argument and find a vertex in here which has no outgoing edge, and we're going to label this Vn minus 1. Then we're going to look at G complement minus Vn minus 1, and again find another vertex which has no outgoing edge, and we're going to call this Vn minus 2, and we continue doing this forever, or n times, so we get vertices Vn, Vn minus 1, and so on, all the way up to V1. Okay, so now that we've labelled these VIs, how is this important, or how is this useful? Well, it actually tells us that Vi is not visible to Vj whenever I is less than j. Well, why is this true? Well, for example, if we look at, say, I equals n minus 1, so we're looking at this Vn minus 1, so we're saying that Vn minus 1 is not visible to Vj for any j bigger. Well, why is that true? So that would mean that Vn would be visible sorry, yeah, Vn would be able to see Vn minus 1, but then that would mean that there's a directed edge from Vn to Vn minus 1, and that's not true because that's how we kind of chose Vn. It was the vertex with no outgoing edge. So this property we have in general, that Vi is not visible to Vj whenever I is less than j. So how can we use this? Well, what we're going to do is we're just going to give Vn the random color. Let's just say red for argument's sake. It doesn't matter. So Vn we're going to give red, or we'll give it blue because the red here looks a bit like a pink. So Vn is going to be colored blue, or the hat's going to be colored blue. So now we're going to give a hat to Vn minus 1. And we want to give the hat to Vn minus 1 in a particular way. And now remember, we're assuming that some strategy exists. Or, you know, we're going to suppose for contradiction that G has no directed cycle. Sorry, we're starting with G not having a directed cycle, and we're proving that it can't have a proper strategy to win, a strategy which guarantees to win. So suppose there was a strategy guaranteed to win. Well, then how would that work? Well, any one of these players or any one of these vertices, their strategy depends only on the hats they can see. That's the only information they have available to them, the hat colors they can see. So Vn minus 1, the only hat it could potentially see, it doesn't necessarily see, but the only potential hat color it sees is Vn's, which in this case is blue. So the only information it has to go off of is that Vn's hat is colored blue. So the strategy will then tell Vn minus 1 to then guess a color accordingly. And let's say the strategy tells Vn minus 1 to guess blue, in which case we'll ensure that Vn minus 1 gets the opposite. So we're going to color Vn minus 1's hat red. So basically we're assigning the colors here, and we want to do it in a way which ensures they lose. And so what we're going to do is look to the strategy, think about what each player would guess based off of the information available to them, and give them the opposite color. And we know that kind of in general, going down this list, any Vi, the only information they have available to them is the color of the hats of the Vj's, where J is bigger than I. So all the hat colors have already been prescribed. So we know what Vi would guess, because we know what Vi plus 1, Vi plus 2, and so on, all the way up to Vn, what the color of their hats are. So once we know that, we know what Vi is going to guess, so we're going to give them the opposite colored hat. And we kind of do this for each of these Vi's, and so none of them have the colored hat which they'll guess. The only potential chance is if Vn kind of randomly guesses blue correctly, in which case they'll win, but of course that's not guaranteed. So if we continue like this, it's impossible for them to guarantee a win, and that's why it's impossible to have a guaranteed win when G complement has no directed cycle. And therefore, if there is a guaranteed win, it must mean that G complement has a directed cycle. Anyway, that solves this problem. I hope you have enjoyed. Thank you for watching, and I will catch you in the next one. Have a great day.